for coming up to my talk. I hope you had a nice caffeine shot for the last 3 to come, I think. I will talk to you about why data science in the medical field, well, both kind of sucks, but is very awesome and rocks at the same time. Yeah, I think I actually changed, I changed my title of the talk, yesterday, I think, in the slides, because I first had AI, but I realized when I was making the talk, actually it applies to data science in general. So data science in the medical field. And why this? Well, I work in the medical field, and I think it's, it has its challenges, but also the medical field, because I think it matters to everybody. Who has never been to a doctor in his life? So I guess it matters to all of you. It has influences on how we are treated, how medicine works, and how we are being diagnosed. And I think a lot is going to happen in the coming years. So that's also what I want to share with you. What is going on? There's a lot of spots back there still, so you can run over if you want. So I think we all benefit from this. And I will tell from my experience and from some people I talked to, from data engineers in the medical field to companies to doctors. But a disclaimer, it's not inclusive or exclusive to only this field, what I'm going to share with you. So as I'm going to tell from my own experience, who am I? I study at the University of Twente, technical medicine. And actually from the time that I did my first Coursera course with Andrew Ng, maybe people know, yes, familiar course, yes. Also my first machine learning course. And definitely not the last, because after that I tried to do all my internships and projects related to data science and machine learning in the medical field. So I worked with, for example, does anyone recognize this, what this is? Nice, yes, ECG, so it's the signal from the heart, the electrical signal, on detecting arrhythmia. But also, for example, on walking data. So I first made my own prototype with my own electrodes and stuff, but this is a bit nicer version that I bought. And we were testing with, for example, Parkinson's patients, because they have trouble walking, and to be able to quantify their quality of gait or walking. Brain signals to detect epilepsy seizures. It's a lot of research has been done on it, but unfortunately still so limited. Clinics actually use these algorithms that I think exist. More on EEG, so on brain signals in Boston on an internship, and there I also used PyTorch. And in the epilepsy project, I switched, that's important, from MATLAB, which I got at university, to the bright side, Python. Well, that changed things, because I think with deep learning and stuff, things go a bit quicker, and I never looked back to MATLAB anymore. And my last project, that's also what I'm going to tell you more about, is about cardiac MRI, so heart imaging. I use TensorFlow, Keras, Google Cloud Platform, and I will use this as a case study to walk through the different issues that you can come along and different challenges within the medical field doing data science. Well, if you might have noticed, if you look at all the pictures that came across, there's, I think, 2 things that are in common, which is medical field and data science. So that's clearly what I like doing. And I'm not the only one with respect to with the machine learning, I guess, and also you guys here. You might have seen these pictures before. It's from Google search. You can actually I made this myself, so you can just type in some keywords and see how the search frequency changed over time. Well, we are here around 2013, and everything started to boom. I think PyData was, 3 years ago? About here, the first raise. But also in the medical field, things are happening. Maybe mostly in research and less in practice, and I will tell you why that's a bit slow maybe. But just some examples. This is a histology example. So what we are looking at is when they take a little bit of tissue out of your organ, so in this case the prostate, to see what kind of cancer you have, or if there's any cancer. And this is what they put under a microscope to detect which cells are what and if they're healthy or not. And there's research going on in automatically detecting these things, because there's pathologists that look at these samples the whole day through. Drug industry, of course, a major industry where a lot of money is invested in. Also, they're trying to figure out new structures of molecules that can work together to have, which they hope to predict that they are effective for certain kinds of diseases. And this one I think is really cool. This is a startup in Nijmegen, and what he does, it's a brain-computer interface. He types with his brain signals. So when he looks at the screen, you see like the letters are flickering, and the brain signals recognize at which letter he is looking at with his own flickering pattern. So it recognizes from the signals in the back of the brain, like what pattern he's focusing on. And I tried it with actually a way smaller headset. They are already having a more compact one, and I had a perfect score. It's like, it works, and it's like, well, you're typing with your brain. It's pretty cool. And this project, so this is my project. It's about cardiac function analysis, and about the automatic analysis of these images, because we want to know more about if your heart is healthy or not. And why would we want to know that? Well, how many of you know someone with heart problems? Yeah, heart attacks or arrhythmia. Yeah, and I think cardiology is one of the biggest departments in a hospital. A lot of heart failure patients exist, and especially in the older range, above 65, the frequency actually increases as well. And the MRI, so the magnetic resonance imaging, we'll just call it MRI, I think also most people actually know that term, is the gold standard for assessing how well your heart is still pumping the blood through your body. And when you want to know that, like how much blood is being pumped out every beat, you need to know something about the volumes in the heart. So what we're looking at here is a slice through the heart. And this is the right heart chamber, and this is the left heart chamber, even though it's at the right. And this is the right heart chamber. And the left one is usually most important because that's the one that actually pumps the blood through your whole body. And the right one does that through your lungs. That's also why the muscle is a lot thicker there. And that's not the most important one to function very well. And well, if we want to know how much blood is in there, we need to know, of course, what the area in here is. So what we could do is contour that. And then we know for this slice in the heart, like around about how big is that? Well, you know, for one slice, I did this in PowerPoint. I mean, they have some tools for that, but it's doable. But what if you have all your slices? So per patient, you usually have around, well, 8 to 15, depending on the scan. And then, what if you also add time to that? Well, that quickly adds up. I should have, to repeat it once more, it's going quickly. Even though it's a very short movie, it adds up to about 400 images for one patient. Well, that's quite a lot of work if you want to do that manually. So we wanted to automate this process of segmenting the different tissues in the heart automatically. And what they can do with this is they can evaluate, for example, medication. So when they have a patient come in, they make a scan and they see what is the heart function. They give medication and then they can evaluate, okay, is it now better? Is it functioning better? Also, for example, for pacemaker indication, to be able to get a pacemaker, you need actually to have a certain degree of having a bad heart. They have to measure it in some way. And to say about, well, what your future might be like, if that's going to be good or bad. And that brings me to the first issue, or the first challenge. And I think we've heard it before, and it's a common one, not only in the medical field, but data retrieval. Where are you going to get your data from? Especially in the medical field if you want to build software as a commercial company. Because is the hospital just going to give you the data? Is it public? Well, there are some data sets, but usually there is bias induced. It might be, not like a very heterogeneous set. And also, what I heard from Wouter, he's a co-founder of PacMed. They are actually a medical software company. He said as well, like, either does not exist, or there isn't enough of it. And an example, in the back, I don't know if you recognize all these images, but this is actually all the small images in the back that were the heart images of one patient. So about the 400 images. And well, we have these 400 images of this one patient, but actually only about 20 of them were labeled. Because it's so difficult and time-consuming to do, they only take the ones that they think contains most information, which is when the heart is the biggest and when the heart is the smallest, when all the blood is being pumped out. Because then they can look at the difference and say, like, hey, so much blood has been pumped out, and that is important to know. So also we encountered that problem, like, okay, we have quite a lot of MRIs, but you know, the label set is a lot smaller already. And yeah, so I'm not the only one with that problem. But what did we do to get data? And that's collaborate. So at the time of the start of this project, I was an intern at Siemens. Now I temporarily work at GoData Driven. It's a bit complicated, but it doesn't matter. The deal is that we were working together. So we had commercial parties involved, but also, very importantly, a hospital. The UMCG in Groningen with Professor Pim van der Harst, who is a cardiologist and very, very enthusiastic about all the new technologies going on right now in artificial intelligence and data science. So he was very willing to support the project and give us the data. And then we also have Google and Binks, who is a Google or cloud provider, if I can say it that way. Then what did we do? Train a network. We wanted to make a model. So it's not going to be a very technical talk, if you might have noticed. So this is the most technical it's going to get, I think. What we did is we have an image sample here, the MRI, and the label. So this is the label for the left ventricle, which is an image the same size as the input, where every pixel is either part of the left ventricle or it's not part of the left ventricle. And from that, we used a model based on the UNet. We tried to actually get an output that, of course, looks similar to your label. So we see that here. This is the map with values between 0 and 1. So this is not binarized yet, like that one. Yeah, and actually, so it's a classifier, but it's a classifier for each pixel. So each pixel gets the class either yes or no part of the left ventricle. And that's why it is weird shape, because it's not just two classes, it needs to become the same shape as the input. And because it looks like a U, it's called a UNet. Easy as that. And we had to train it, and we decided to train it as, yeah, you saw one of our collaborators was Google Cloud, in the cloud. Well, if you tell in the medical field, like, hey, yeah, we're going to do things with the cloud. Oh, really? Okay. But actually, by law, it's allowed. You don't need extra consent from a patient to put your data in the cloud. So even if it's not anonymized, you have to keep it safe, of course, but you can do it. You don't have to ask the patient, like, oh, is it okay if we put your scans in the cloud? So it is allowed. And actually, what I see in a lot of startup business models is that make software in the medical industry, they actually do use the cloud. So they send right away from the scan, they can send things to the cloud, analyze, and return answers. So that's what we did. We used it, we trained it, and what you get out is, of course, the predictions. Yeah, so the results. We actually, in the end, made 3 networks for the 3 different structures. And we had a DICE index, which is like a metric for similarity. It doesn't really matter what it means, but it was for the left ventricle was the easiest. It was about 95%. And the right ventricle and the myocard was a little bit lower, about 58%. But what does that actually mean? Like, is that our validation? Yeah, anyone recognizes this? Anyone watch this? Wow, one brave guy. I don't even know if it's still on TV. Is it? Thanks for the honesty. So what does that even mean? I mean, if my algorithm works because it shows 90% accuracy, then is it a good algorithm? I mean, it kind of depends on what data you use, of course. And we talked about it before, like, is it a very homogeneous small data set that you can overfit to? Or is it representable for your whole population? And in this case, for us, for example, it's very important. Like, actually, the data set we have now, which is funnily, we used MRIs from Philips. I was intern at Siemens, but all the data came from the MRI from Philips. But, you know, does it also work on different machines? And also, all our patients were infarct patients, so they all had a heart attack. But what does it do in healthy patients? So we can have, for example, a 90% accuracy, but yeah, what does that actually mean? And another thing is actually, like, if you could compare it to, for example, if you want to make a model to predict who is missing their flights or who's going to miss their flights, it's pretty easy to say, well, they're on that plane or they're not. There's not really anything in between. But doctors, well, they can differ in their opinions. And for example, with our case, what you see here is there's this little bumps. I don't know if you see it, yeah, with the arrows. And these are little muscles that are attached to your heart valves. And, well, some say, yeah, that's part of the blood volume. That's like, it doesn't matter, we can just put the contours here. And others say, no, 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 no. Where muscle is, there's no blood. So we have to go around it. So you already get two different answers for the same question. So if I get a 90% accuracy, who do I even compare it to? Is that compared to the one radiologist or the other? And, well, you can imagine that asking 10 radiologists to do this for you is kind of expensive. But this is a real problem in a lot of medical problems, because there's not always one right answer. And here is also the results of what you see here is the ground truth of the percentage of blood being pumped out at every beat. And these are all the data points of our different patients. Yeah, and this is our prediction. So if it's on the middle line, of course, it would be perfect. But I was looking in some literature about what is the interrate of variability, they call it. So if I would ask 10 radiologists, how much would they differ? And it's around 5%. And these are these red lines. And my standard error was I don't know if they're really clear, but the light gray lines. And they're really close together, actually. So, you know, what does this mean? Am I perfect? Am I just as well as, you know, one radiologist? Or, you know, yeah, when is it good enough? So once you have a model is nothing. I mean, a model is nothing unless you can use it. So the next step would be to productionize. Go from your model to actually something a doctor can use, because they're not going to go into TensorFlow and say load MRI. That's not going to happen. So you need some people that can actually do that. Yeah, but this is a quote from the professor that we work with. And he's like, yeah, you know, it's just simply easier to make money in a different industry. So this is about, I think this is twofold. It's not only about, you know, if I want to make a software product, well, you could have second thoughts about, you know, going for the medical industry all the way, because it can be a long trajectory before you get back your revenue or to get back your investment. And, you know, you might choose, well, let's do something a little bit easier. And the second thing is, where would you work? There's, I think, different industries that are easier to, or where higher salaries can be gained than maybe in research or in the hospital. So to get high-quality people on board, data engineers, data scientists that can do this, software engineers, is, I think, a bit harder as well. This is actually a quote from our host, Priyanka. She's data engineer at the Dutch Cancer Institute. And what she said was like, we lack a centralized IT vision leading to data silos. And I think this is a very good demonstration of how complex the hospital structures are, because it's pretty isolated and financial flows are complicated, and you know, you're dependent of subsidies a lot. So if they have this group that we are working together with this one professor, and he's really enthusiastic, and he's getting all the money in, and you know, he hires a PhDer to do something for him and to do data science. But yeah, then he gets money for 4 years for his one PhDer, who is very good at doing data science. But then maybe he wants to build a product. But then maybe he needs a data engineer, a software engineer. Yeah, but there's no money for that. And he is there for 4 years. So who's gonna do that? There's not the entrepreneurial mindset or drive that could be there commercially. So I think within hospitals, it's pretty difficult to get things going and get things to really be productionized. Well, I gave it a try. For me, actually, the same reason. Because of contracts, also bureaucracy in the hospitals, as I said, complex structure, it's really difficult. It took a long time before the guys from Go Data Driven and the real technical guys could join the project and work with me. I kind of had to do it by myself. And yeah, I'm not a software engineer, but I tried to make some prototype interface in Python. This is with PQT5, if you say that correctly. So what we see here is how the heart volumes change. So the blue line is the left ventricle, and this is 1 heartbeat. So you can see here, it's completely filled with blood, and then it's pumped out, and it fills again. And the green line is pretty flat, which is good, because it's the muscle, which should not disappear during a heartbeat. That's a good thing. It's a check, then you know that you're not doing really stupid things. And here's some features that doctors look at often, and yeah, there's, it changes when you click. I was really proud of that. Like, oh yes, it works. I mean, everybody can recognize that, right? When you have this thing that you actually don't know how it works, and then it's like, yes. But in the end, luckily, we got the contracts going, and some guys actually made it more fancy with a web app. So now, actually, you guys can type in this, and then you can choose some patient number. We don't have all of them until 223, so they won't all work. But and it gets the data right from Google Cloud. And yeah, you can pretty much do the same thing. It's not that much different. But it already looks a lot better. Then, when you have a product, implementation. How do you get it there where you want to have it? And how? Mostly, how are you going to get it there? Because we've been building on an app for heart function analysis. But if we look at the position of a radiologist, he's not only looking at hearts, he's also looking at brains and prostates and livers. And so are they going to have some sort of app store? And like for every patient, they have to click something else, and then scrolling is once with the arrows, and then it's with the mouse. And I cannot imagine that's going to be the best way to do it. Or do we need, maybe this little comic, do we need one standard? And should we ask Philips or Siemens? Should we lean on them to make all the software and implement that in their machines? But I guess, it's a big organization. That's damn slow. So I don't know the answer. If anyone does, please let me know. And because I'm really thinking about what is the best way to, make this work. And speed up things a bit in the implementation of all these cool data science and AI research that's being done in different fields, but then to also implement it in the medical field. Last but not least, for sure, the acceptance, because doctors, they are kind of stubborn. I don't know if I'm offending anyone. Any doctors in the room? Which makes sense, because they have a large responsibility. If you compare it to, for example, a factory worker or a factory, and the manager decides oh, we're having too many machines breaking down because of failure by the employees. They say, okay, we're going to use this computer vision tool, and it's going to detect when something needs to happen. And they just have to deal with it. And if it works or not, this manager will be responsible. And he will feel whether things have gone right or wrong. But if a hospital tells a doctor, hey, yes, please, we have this cool new tool, use it, please. And yeah, it will save us money. Then who is responsible when there's a mistake being made? It's not only the hospital, it's the doctor himself or herself. So it makes sense. I mean, it's not good for this industry, but it makes sense. They have a lot of responsibility on their shoulder. Yeah, this suits it. This was a comment made also by a medical software company, and they have a CE certified product, so it has its label, and they can sell it. But what they hear a lot apparently is yeah, sure, but please let us validate it first too. And then, maybe we'll buy it. There's just little trust still in what's going on and to invest in it. And, well, to invest in it there is, but to really, use it. And last, something that is in many, I don't know, my LinkedIn at least, comes along all the time with blogs and stuff like, oh yeah, the jobs of radiologists are going to disappear. Well, a couple of months ago, I talked to a retired radiologist, and I was thinking, like, what was radiology like 50 years ago? Oh wait, there was no MRI, there was no CT. Well, that changed. So I think it's these comments about technology, like, oh, everything's going to go wrong now, is just, I don't know, stupid or something, if I can say it that way. But, you know, things are going to change, but it always has. Technology has changed things. It has made jobs disappear, but it also has created new jobs. And radiologists, you know, these days, because of the things we can do with all these imaging techniques, we use them more. I mean, the amount of MRIs being made every year is just increasing. So we also need to find a way to make the analysis more efficiently, so we can process all this new data that comes to us. So I think it's just going to change, but it's not going to disappear. So for anyone knowing radiologists, please ease their minds. So in short, the different issues that I addressed, yeah, again, it can also definitely address industries you work in, data retrieval, validation, and certification of your algorithms, to actually productionize it, implement it, and to actually have people use it. Yeah, so there's many challenges that this industry faces, but there's one thing I can tell you: data science is going to change a lot in the medical field. It's going to change the way we diagnose. So, for example, well, here we see someone listening to the heart. Is it going to be a doctor, or is it just going to be a machine or an algorithm, or just a recorder that is going to say, like, hey, your heart sounds like arrhythmia? Yeah, and the way we treat. Are we going to trust the knowledge of this one doctor sitting in front of you? Or would you rather have an algorithm trained on, you know, all the experience in the world and know, like, oh, this treatment would probably work the best for me regarding my profile? And the role of a doctor, I think this is an interesting one. Who is going to be the second opinion? Is the doctor going to be the second opinion of the algorithm? Or is the algorithm going to be the second opinion of the doctor? Maybe it's a volatile process, and we'll see where it's heading. I think it's a really interesting, yeah, industry, and I will stick around in it hopefully for a while and try to push this innovation forward and yeah, try to improve healthcare and use data science for it. And I hope I didn't demotivate you too much, but actually also motivated you to maybe come along with me on that journey, because hey, challenge is also fun, right? So if you actually are up for the challenge and working with this data, a little commercial, but the Dutch Data Science Week, we are doing a hackathon with this data set. We have 2D, 3D, 4D data, so for everybody something in different levels. Sign up is still open, so yeah, DutchDataScienceWeek.nl, and you can still sign up for it. Thank you very much for listening.
Thanks, Kicky, that was wonderful.
Thanks.
Any questions?
You're using open source tools all the time. Do you see any role for open source in the, say, the core software that hospitals use? Because from what I understand, all of them have different software stacks. Yeah. There's no interoperability. It's very hard to get even the data out of the systems. Whereas a lot of the university hospitals have adjacent, say, IT training. It seems like there's such a, it's not their core business to sell software or stuff. So it seems like this is such a missed opportunity always, what I think. Is there any progress in this area?
You mean to get the hospitals more IT-ish in open sourcing things?
They use open source stuff themselves.
Oh, okay, the other way around. Yeah, I think I wonder, because I think hospitals are very, you know, having a CE, well, they have to also, like CE certified tools. These things are very important. I mean, you cannot just give it, make software that diagnoses disease and not have it approved. So I guess you need to, you know, it's hard to match maybe with open source. And I think definitely with the larger IT systems, there's so much investment going into that, like the chipsoft, and to build that's pretty hard. But yeah, maybe small things. I mean, in research, yeah, researchers are using TensorFlow and all these things, obviously. Yeah, like me. But yeah, I don't know if that's gonna be soon.
Yeah, we at NKI are using open source, but for research.
Yeah, for research. Yeah, that's the cool thing. Yeah, there's a lot of libraries on EEG analysis and things. Definitely, yeah, research is a lot easier than when you want to do it clinically, because that avoids a lot of rules. Because then you are still responsible of, well, is this good enough or not? But it doesn't have consequences yet. So that's a different thing. Yeah, research a lot. That is happening. That's changing quickly, I think. Yeah. Thanks for adding on.
Any more questions?
In the back there.
Yeah, thanks. Thanks for the talk. Very interesting. I was wondering if you could elaborate a little bit on storing data in the cloud, because like I work for the University of Maastricht, and I have also often data from healthcare registries, information systems, and pseudonymized. Am I allowed to store that in the cloud, or is that still?
Well, if you have the consent from the patient, right, that you are allowed to have the data.
It works on a no objection basis. So the whole GP practice participates.
Yeah.
The GP gave permission.
Yeah, so the general practitioner, you mean, right?
A general
Yeah.
practitioner, yeah.
So the doctor, yeah.
And he has on his website declaration that he participates in scientific research and that people can
Opt out.
Opt out, yeah.
Oh, that's difficult. I'm not sure about these rules because I mean, if you give consent, usually about like I'm attending this research, I give consent, you can have my data and use it for research. Then where you store it is up to you. Yeah. So you need to make sure it's safe, but whether you keep it safe on the cloud or keep it safe on a server, that's up to you. Yeah, in this case, like, so I assume it's the same thing, but I'm not sure about the opt-out, opt-in.
Yeah, you have individual informed consent
for
every patient. Yeah.
Well, but yeah. But also, even if they don't give consent so if it's consent for clinical purpose, so for example, a patient comes in and they have their scans made because they just need it, then also it can be put on the cloud. Okay. So, I mean, consent is for the research purpose, but you can store it on cloud, yeah, when you just, as a storage.
Thank you very much. Yeah.
One more last question.
Here's one.
With these CT scans data or MRI scans, I saw another application where you can warp the data and use that to vastly augment the data. Because you can't warp a car, straight edges are not going to be straight anymore, but you could do it with a heart, I imagine. Does that work that way? To
augment data, you mean?
Yeah.
Yeah, to like generate more data?
Instead of just rotating and flipping it, also warping.
Oh yeah, I did that. Yeah, I don't have the slide in here, but I definitely, I warped it. Yeah, we did augmentation with some warping, with contrast enhancement, cropping. Yeah, definitely. So we increased our size amount of data, but augmentation is still a way, but it's not all. Like, yeah.
Thank you very much.
Thank you very much for listening. Oh,
one more
yeah.
round.
Oh, what's one? Yeah, let's finish, right?